A research breakthrough from the University of Technology Sydney, UTS, has demonstrated that a long-dismissed method for establishing quantum communication links with satellites is, in fact, feasible. Published in the journal Physical Review Research, the study titled Quantum Entanglement Distribution via Uplink Satellite Channels overturns the conventional wisdom that quantum signals must be generated in space. Led by Professor Simon Devitt and Professor Alexander Solntsev, the team's work proves that entangled particles of light, photons, can successfully be sent from Earth to a satellite, creating a viable uplink for quantum communication. Traditionally, quantum satellites like China's pioneering Messius and the more recent Jinan-1 have operated on a downlink principle. They generate pairs of entangled photons in orbit and beam each particle down to separate ground stations. This method, primarily used for ultra-secure quantum cryptography, requires only a handful of photons to create encryption keys. The reverse process, producing entangled photons on Earth and transmitting them upward to a satellite, was widely considered impractical. Scientists believe that atmospheric interference, scattering of light, and significant signal loss would render an uplink impossible. The UTS team challenged this assumption through sophisticated modeling. They simulated the highly precise scenario of firing two individual photons from separate ground stations to meet at a satellite orbiting 500 kilometers above Earth, traveling at roughly 20,000 kilometers per hour. Crucially, their models incorporated real-world complications, including background light from Earth, sunlight reflections from the Moon, atmospheric turbulence, and imperfections in optical alignment. Surprisingly, the results indicated that achieving the necessary quantum interference between the photons in space is feasible. This finding has profound implications for the future of quantum technology. It removes major limitations of current satellite systems. Ground-based equipment can leverage greater power resources, is easier to maintain and upgrade, and can generate much stronger signals than compact satellite hardware. These advantages are critical for moving beyond simple cryptography toward a full-scale quantum internet. As Professor Devitt explains, connecting future quantum computers via satellite relays will require vastly more photons and bandwidth than current cryptographic applications. The uplink strategy offers a practical path to this bandwidth. The satellite itself would only need a relatively simple optical unit to interfere the incoming photons and relay the results, rather than housing the massive power-hungry hardware required to generate trillions of photons per second in space to overcome downlink losses. This approach promises to keep satellite costs, size, and complexity lower, enhancing scalability. The research outlines a near-term testing path using drones or high-altitude balloons as receiver platforms, paving the way for eventual networks of small, low-Earth orbit satellites. Such networks could form the backbone of a global quantum infrastructure. Professor Devitt envisions a future where quantum entanglement becomes a ubiquitous utility, akin to electricity, an invisible commodity generated and transmitted to power advanced devices. Users would simply plug their quantum computers into this entanglement network to perform complex tasks. This interdisciplinary project, combining expertise from UTS's Faculty of Engineering and IT and Faculty of Science, showcases how collaborative research is tackling significant challenges in emerging technologies. By proving the viability of the Earth-to-space quantum uplink, the work opens a more practical and scalable avenue for building the long-envisioned quantum internet, connecting nations and continents through secure, high-bandwidth quantum links.